Dear students, welcome to the next topic from electrostatics, which we call it as application of Gauss's law. Last class we have learnt what is called Gauss's law, and today we are going to see what are all the things which we can where we can use this Gauss's law to find out electric field. Okay, so we'll go to application. Application means where we are actually using this law. Okay, so the first use case of this law, so write on the first heading, the first use case, electric field intensity. We are going to find out electric field. Electric field due to a infinite charged wire. Infinite charged wire. Electric field due to a infinite charged wire. This is the first applications. We are going to find out electric field for an infinite charged wire using Gauss's law. Okay, it's not mandatory that you have to use Gauss's law, but this is quite easy to use this law and to find out the answer. So let's move forward. So I have a conductor or I have a wire. Okay, this wire will contains what charge? Positive charge. You can assume positive or negative, it doesn't matter. Okay, so if this wires contains charges, what will happen from here? Electric fields we are going outside in various directions, right? Electric fields are going always outside, both positive and negative. Always it is going to all surroundings, but because it contains the charges, so electric fields are going at various directions. So we are going to use Gauss's law. What is Gauss's law? States that closed integral E dot dA equal to Q divided by epsilon 0. So Gauss's law states that if you want to use this law, we need a closed path. We need a closed path. So this is not a closed path, this is a wire. So in that cases, we have a provisions here, which means we can consider a Gaussian surface. Gaussian surface is a closed surface where that surface is a closed surface. Actually, there is no Gaussian surfaces, but in order to use this law, this circle is saying I need a closed path. Wire is not a closed path, it is just like this pen. Okay, so I need a closed path, something like a cylinder. So I am going to assume a closed path will be here, and this is my closed path. This blue color is closed path. So this closed path is looks like what? It looks like a cylinder. It looks like a cylinder. Okay, so I have assumed a Gaussian surfaces. Now from here at a distance of r meter away, okay, at a distance of r meter away, I am going to find out electric field. So this I can say I am going to find electric field due to a infinite. So this is plus infinity and this is going to minus infinity. So plus infinity to minus infinity, one wire is placed at a distance of small r meter away. I am going to find out electric field. Electric field due to an infinite charged wire. So for that we have assumed a Gaussian surface. This blue color stuff is called Gaussian surface. Gaussian surface. This is nothing but an imaginary surface we are assuming to do this, to use this Gauss's law. So we will apply, will be here. So we have how many surface will be here? If it is a cylinder, means top one plain plate will be there, bottom one plain plate, and it is a circular plate is there. So totally three things will be there. Surface number 1, surface number 2, and this is surface number 3. S1 and S2 are plane surfaces, like, okay, and S3 is nothing but it is a curved surface in a cylinder. So I can say closed surface is formed because of many open surface. This is a plate. Okay, so I can say this is nothing but we call it as flex. Flex will be equal to Q by epsilon 0. So there are different surface will be there. So for the surface number S2, EDA, here electric field. So in these surfaces, with respect to this surface, electric field, with respect to this surface, electric fields are going like this, and the area vector for this surface, this is the area vector, dA vector, and this is the electric field vector. So now this I am considering as an open integral, because for one plate it is open, S2 is open, S3 is open, S1, S2, S3 all together will form. This is like S1, S2, S3. This is S1, S2, S3. S1, S2, S3 all together will form a closed path. So here we have only one path, S1. So that is open. and E dot dA, which means EDA. What is the angle between electric field and area vector will be here? Cos 90 plus second one, open integral one surface S2. S2 is also what? Electric fields are like this, and this is our area vector is like this, area vector. So angle between them is 90 degree. Here also angle between them is 90 degree. So it is EDA of cos of 90 plus. The third surface we have, what is the third surface we have? Open integral of S3. This surface area vector is like this. So what is the angle between electric field and area vector? Electric field is like this, outside going away. So angle between electric field and area vector is 0 degree. So EDA into cos of 0. This all together if I am adding and equated to what called Q by epsilon 0. Now we'll see. Cos 90, this term goes to 0. This term goes to 0. This is 1. So we have only one factor. So these two are going 0. So now our integral is EDA. So we have an integral. Now all together it's an integral of on surface S3 equal to Q by epsilon 0. So E into, what is the surface area of a cylinder? Surface area of a cylinder means its radius, correct? So its radius, suppose I am going to find out electric field will be here at a distance of r meter away. So integral S3 into area of this cylinder will be equal to what? 2 pi r into L. This is the area of the cylinder. Okay, small classes we have learned, right? Q divided by epsilon 0. Okay, so E will be equal to okay, so the dA integrated we got 2 pi r. So E will be equal to Q divided by epsilon 0 into 2 pi times of RL. Q divided by epsilon 0 into 2 pi times of RL. Here we have already learned one term is called linear charge density lambda. Lambda means what? Lambda means charge divided by length. So here charge divided by length area, I can substitute lambda. So what will come? Lambda divided by 2 pi epsilon 0 times of r. R is the distance where at which I have find out the electric field intensity. So this distance is nothing but r. Okay. So I'll go through these derivations once again for your better understandability. I have a wire. I need to find out electric field intensity. Okay, so for this I don't have any Gaussian surfaces, which means a closed surfaces. To have a closed surfaces, I have assumed a cylindrical structure over this wire, which contains S1, S2 and S3. Three surfaces will be there. So the closed integral split into three open integrals, S1, S2, S3. S1 is the topmost area, S2 is the bottom area and S3 is the side areas. Electric field lines are emerging out like this. Electric field lines are going right, going left like this. So with respect to S1 surfaces, electric fields are going like this and area vector is like this. So the angle between them is 90. With respect to S2 surface, area vector is like this and electric field like this. Angle is 90. So this is cos 90. With respect to the curved surfaces, electric field like this and area vector is perpendicular to the surface. So the angle is cos 0. And S3 is alone remains there because cos 90 is equal to 0. So these two terms going out. And we got E dot dA equal to Q by epsilon 0. E dot dA dot will be replaced with the cos term and we have cos 0. We are integrating dA, the small area if you are integrating. What is the integral of dA? Integral of dA means integral of the area of the cylinder. Okay, area. Integral of dA means A. What is A? What is A is called area of the cylinder. What is the area of the cylinder? 2 pi r, its radius into its length. Here I assume the length will be equal to L. So r is the radius, L is the length. So 2 pi r Q by epsilon 0. Electric field formula we have written, which we have learned about charge divided by length is called lambda. Lambda is called linear charge density. Based on that, E is equal to lambda divided by 2 pi epsilon 0 r. This formula is very important because while doing the numericals, normally for your school board examinations point of view, this model of derivations, may ask. So understand the concept. We have totally 3 surfaces, 2 surfaces will cancel out and 1 surface will remains there. and we find the electric field intensity due to an infinite charged wire. Where in an entrance point of view, the questions are coming is based on the numericals. Numerical questions are coming based on this point. So there we have to find out, there we have to know what is called lambda, what is 2 pi epsilon 0 into r. Hope you remember the value of epsilon 0. Epsilon 0 equal to 8.85 into 10 power of minus 12. If you are not remembering, try to note down this value, 8.85 into 10 power minus 12. This is a value of epsilon 0. Epsilon 0 is for a free medium or an air medium or a vacuum space. That is called epsilon 0. First class itself, when we are discussing about Coulomb's law itself, we told about this factor, right? So this is the derivations, and this is a formula. This formula is very important. You have to remember. Definitely there are questions are already came, and you may get some number of questions based on this areas. Okay, with respect to a wire, with respect to a single wire at a distance of r, electric field will be equal to 2 pi epsilon 0 times of r. Okay, let's move to the next session. So totally we have to see 3 areas we have to see will be here. So this is the first one, electric field due to a infinite charged wire, and we have to see the next derivations part, the next thing. So write on the next second applications. Now we have find out electric field due to a wire. In third applications, we are going to find out electric field due to a cylindrical structure like a pipe. Pipe means a normal PVC pipe. Normal PVC pipe, anything is inside? No, it is empty, right? So that is our second applications. I am sorry. Second applications, electric field due to a solid conductor. Solid conductor means the meaning is inside it is empty, or it is also called hollow conductor. Solid conductor, or it is also called hollow conductor. Okay, solid conductor or hollow conductor, which means inside it is empty, inside no charge. So I can say inside empty space. Inside empty space. Okay, inside empty space. So let me consider a cylinder like this. So I have a cylinder like this, and I am going to find out the electric field area at 3 different positions. One is inside, okay, and the other point is at the surface, and the other point is electric field at outside. So this is a cylinder and whose radius will be equal to r. I am considering with respect to the central axis, I am considering an inside point called r. So in order to apply the Gauss's theorem, what are the things I required? I required a closed surface. So this cylinder is itself is a closed surface, but with respect to an inside point, there is no closed surface. So I need to have a closed surfaces inside the cylindrical structure. So we are going to consider a closed surface will be like this here. This blue color is a closed surface. So with respect to the closed surface, now it's a closed surface means you can consider a small cylinder within the bigger cylinder. So this is actually our closed surface is like this. Our closed surface is like this. Okay, so our closed surface is located like this. This is a small cylinder inside. I told here charges are present only at the surface. Inside it is empty. So charges is present only outside. So here with respect to this surface, as I told before, there are 3 surfaces will be there. This is called S1, and this blue color is called S2, and the inner side, inner curved surface is called S3. We already know electric field at S1 surface will be equal to 0, S2 surface will be equal to 0, only S3 surface are exist. So we are writing closed integral EdA equal to Q by epsilon 0 dot product. We are expanding, we know S1 0, S2 0 from the previous derivation. I am not repeating it again, so we know only the third surface. So EdA of cos 0 for S3 surface alone, because S1 and S2 is already gone, is equal to Q divided by epsilon times of 0. Okay, here we have to write some terms. Here E is a constant dA. What is the integral of dA? If this radius is small r, then the surface area is equal to 2 pi RL. This is called the surface area, and which is equal to Q divided by epsilon 0. Q divided by epsilon 0. So electric field E will be equal to Q divided by 2 pi RL multiplied with epsilon 0. Here we are going to introduce one term, and that term is nothing but it is representing 2 pi RL. This 2 pi RL term is called sigma. This 2 pi RL term is called sigma. Sigma is it is nothing but called surface charge density. So I am going to write the term called surface charge density. So that is called surface charge density. So the term sigma is called surface charge density. Hence we can written as we have some linear charge density lambda. Lambda is called charge by length. Surface charge density means charge by area. So this Q by epsilon 0 is called sigma. So E will be equal to, the final formula is sigma divided by epsilon 0. If you have doing the derivations, I will say this is an incorrect way. Okay, what is the major problem will be here with respect to this part? This is pakka wrong answer. Why? Because as I told, this is called a solid conductor or hollow conductor, which means that what? The charges are present inside. Inside any charges are present? No charges are present. So inside no charges are present. Inside no charges are present means what is I told when I am taking the Gauss's law? This is called Q enclosed. Any charges are within the Gaussian surface here? No charges. So of course, what will happen in this case? This term will be equal to 0. If this term will be equal to 0, we cannot write all these steps will be here. If that is equal to 0, I can say electric field will be equal to 0. This is the right steps. So always we have to see whether we have any charges are present within the device. If no charges, we cannot do. Now instead of taking this point will be here, I am taking the point at the surface. So this will be coming as R. So in this case, now this is an inside point, right? This is inside. Now if it is a surface point, we are going to find out electric field at surface. What will be changes? Again for surface means S1, S2 and S3 areas will be there. And if you are doing like this, what will come? Will be E into 2 pi times of what will come? RL, capital R, because the radius is I have measured as capital R, into Q divided by epsilon 0. Here Q is applicable if you are finding at the surface because charges are present on this Gaussian surface. Now with respect to our Gaussian surface is a cylinder. So electric field will be equal to, we know, Q divided by 2 pi times of RL into epsilon 0. Charge by area is called, as I told before, sigma. Sigma divided by epsilon 0. This is the electric field intensity at the surface. Electric field intensity inside will be equal to 0. Okay. Okay. Next, we are going to find out electric field at some other point. We are going to find out electric field at some other point. At some other point means we are going to find out electric field at outside of the cylinder. So what will happen if you are finding outside? Outside means I am going to calculate outside here. So with respect to this point, we need a Gaussian surface. So I consider a Gaussian surface like this by including the outside point. That distance I have considered small letter r. You can take any variable. It doesn't matter, but small r I have considered here. So again we have S1, S2, S3, everything will go, and we have to see whether any charges are within this big Gaussian surface. Yes, within the big Gaussian surface we have a small cylinder is there, so charges is already present in the cylinder. So we can say only S3 surface will be here, of course. So EdA of cos of 0 will be equal to Q divided by epsilon 0. This is at where? At outside. We are going to find out outside. So surface we already find. So this is for outside. So outside. So E electric field. What is the area of this outside cylinder? Outside cylinder is 2 pi RL will be equal to Q divided by epsilon 0. Okay, here the charge divided by the surface area of this cylinder is given as sigma. Okay, now we will see E is E into 2 pi RL. Here we are multiplying, we are changing this Q. As I told, Q divided by 2 pi RL is called sigma. So what is Q will come? We'll write it here. Q divided by 2 pi RL. This is the original cylinder radius R. Original cylinder. The outside one I have assumed. That assumed one is called what? Called Gaussian. This is called Gaussian surface. This is called Gaussian surface. This is not the one I have assumed. It is outside. So this Q is equal to sigma. For Q I am substituting. What is coming? Sigma into 2 pi times of RL divided by epsilon 0. Okay. So 2 pi L cancel. 2 pi L got cancelled. So E will be equal to sigma capital R divided by epsilon times of R. This is the electric field intensity at outside point. So 3 points we have seen. Electric field inside equal to 0 and electric field at surface equal to, surface means this R will come to this point, which means small r equal to capital R. R and R get cancelled. We'll got sigma divided by epsilon 0. Okay, and E at outside point, electric field is equal to what? At outside point, electric field is sigma capital R whole divided by epsilon times of R. So these three formula, whatever we have written here, you have to remember. This is for a hollow conducting sphere. Normally if in a question it is saying like that, solid conducting or hollow conductor. If some such statements are there which indicate charges are present only outside. That's what, if you are considering any Gaussian surface within the cylinder, we are getting charge equal to 0 and electric field inside will be equal to 0. Surface we have electric field because surface charges are present. And outside, if I considering the outside, within that bigger cylinder area, we have a small cylinder inside. So first we look any charges are present within our Gaussian surface. Yes, then we can proceed. If no charges are present, first stage itself we can say electric field intensity will be equal to 0 at inside, surface equal to sigma by epsilon 0 and outside will be equal to sigma R divided by epsilon R. If you remember this formula, you can do it for anything. Electric field intensity outside, if you are remembering, if it is surface means what is the value of small r? This surface means from here the distance is small r. Surface means this r will come to the surface position. What is the, so small r equal to capital R. Then r and r will get cancelled. You will get surface formula. Inside means you know there is no charges. So electric field intensity is equal to 0. This is a second applications of Gauss's law.